Okay, so that's lecture number 9 from Math 2400, and that is negative binomial distribution. So let's see what this is. So this is very simple. So you play a game. So probability of success is P, and probability of failure is 1 minus P. Okay, so, and that doesn't change. The success and failure, they don't change, and you let X be a number of failures before X successes. Well, I don't say X, that's right, and something else, because this is R success. Right? Okay. So you play a game, boom, 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 boom. So you have like failure, success, success, say failure, 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 dot, 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 and you assume that you have R. So when you have R successes, it means that the last one is also a success. So the last one is a success, and that is R. So we say, I play this game until I have 20 wins, say, something like that. And then I will stop. And you want to see how many such, you want to see how many failures, I mean, not how many, what is the probability of having certain number of failures before, say, 20 successes, okay? So you want to see if what's the probability of just one failure before, let's say, 20 successes or something like that. Now, these successes and failures are dispersed here, so it doesn't mean that you have fail, 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 and success, S, 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 S. No, they can be anywhere. Okay, let's see. This is like that binomial again. Like binomial, I can analyze this step by step. So let's say I have one configuration here. One configuration. So I have one configuration. Configuration number 1 will be, I don't know, something. And that something is, say, so I don't know what that is. It might start with a failure, it might then go success, success, failure, dot, 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 and the last one is success. So I have R. Okay. And I have R successes and X failures. So, what is the probability of this thing happening? Just this configuration. So the probability of this configuration happening is not that hard because I have R successes, so it is P to the power R 1 minus P to the power X. Okay? P to the power R 1 minus P to the power X. Then, how many cases like this do I have? Okay, if that X is just fixed at X, then I have other configuration 2, dot, 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 and configuration, say, question mark. So how many such configurations can I have? Well, it's not that hard. Just look. I have, the last one is always S. So I'm left with how many here? That is, the total is R plus X minus 1, because the last one is S. Then out of this, I have, say, in this, there's one success out, so I have R minus 1 successes. Okay, so it's like R plus X minus 1, choose R minus 1. So I'm just throwing some balls, say R minus 1 balls, and each of these holes takes one ball. So I want to see in how many ways I can put like balls in these R plus X minus 1 holes, R minus 1 balls, right? Something like that. So what is that? We have done this a lot. So that question mark is in fact C, the combination R plus X minus 1 and R minus 1. Or as we have written this in this form. Okay. So I have this many configurations, and each one has this probability. So the probability that X is in fact, just put all of them together. Why? Because this event, I have this many events and they are mutually exclusive, right? So I just put, when I say probability of this, or this, or this, or this, and so on, it will be probability of this, plus this, and so on, because they are mutually exclusive. So let me erase this and write it here. So I need probability that configuration 1 happens, or configuration 2 happens, or or the configuration question mark happens. And they're mutually exclusive, so that's configuration 1 plus probability of configuration 2 plus up to probability of configuration question mark, and that's the number. So I will get R plus 1 minus R plus X minus 1 over R minus 1 times that. And the probability of each configuration is fixed. It doesn't change from configuration to configuration, it's the same thing. Okay, so that is probability that X is in fact small x. X was number of failures, is small x. Okay, so this is in fact the negative binomial, and you saw that the way that I analyzed this was similar to the way I analyzed binomial distribution. Okay, now special case is what we call a geometric distribution. So let me erase this and write the special case for you. So geometric distribution is when number of successes is just 1. So you just say, okay, I will play until I win just once, and then I stop. So, well, that's okay. I'm not a gambler or something. Maybe that makes sense to those who are professional gamblers. So they just go like this, boom, 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 boom. So the last one is S, and they're all failures. And stop. So in this situation, R is 1. Oh, okay. Stop. Let me. Okay, so if I have a this is x plus r. Yeah, so the probability that I have x failures will be, I remember that was x plus r minus 1, so it will be x and r minus 1 is 0, say, and what's going on? Now let me double check. So that one of them will be p times 1 minus p to power x. It's not x. R is a number of stuff. No. Okay, so that's simply p times 1 minus p to power x. But that's okay. If I write x0, I will get 1. Okay, so x0 is 1. So that is a geometric distribution. Okay, so let me write down the expected value for the negative binomial, and you can just derive expected value from this, which is not that hard. And in fact, this one is easy because it goes back into maybe college algebra. You can use college algebra to find it. So for negative binomial, so if x is a negative binomial, then expected value of x will be, well, let me just copy it. I can derive it, but it's the way that you can derive it is using, again, Bernoulli, and write negative binomial as the sum of some Bernoulli distributions, and then just add them. And the variance is also a nice formula. It is r times 1 minus p over p squared. So for the geometric, if I have x geometric, and usually they write them as p, this one you can also write negative binomial p, and then e of this x will be, that's when r is 1, so that's 1 minus p over p, and the variance of this will be 1 minus p over p squared. That's when r is 1. This is r is more than 1. Okay, so that is in fact the story of negative binomial distribution, and the special case is a geometric distribution. Okay, so let me stop this.